Get ready to blast off into the incredible world of brain-computer interfaces. Neurocareers doing the impossible is taking you on a journey to meet the fearless pioneers pushing the boundaries of what's possible. In this special series, we'll be shining a spotlight on the nominees and winners of the International BCI Award, one of the biggest and most prestigious awards in the BCI world. You'll hear from BCI professionals as they share their revolutionary work and get a behind the scenes sneak peek at what it takes to be a winner. So, buckle up, grab a snack, and get ready to be amazed as we explore the impossible becoming a reality in the world of BCIs. But before we blast off, I want to give a big thanks to the co-host of this BCI Award edition on our podcast, Dr. Christoph Guger and GTech Medical Engineering. When I was a faculty member at the University of Cincinnati and Cincinnati Children's Hospital Medical Center, my team and I did some pretty amazing stuff for patients needing epilepsy surgery. We would put special sensors, also called grids, directly on their brain to prepare for surgery and create maps of their brain in a much faster and safer way than is usually done. It's called high gamma mapping, and it lets us figure out in just a few minutes the essential parts of the brain that need to be spared during surgery. Can you imagine? You can create a map of language, motor, and even math processing in no time. It was the first time this innovative technology was used at Cincinnati Children's Hospital Medical Center. When I moved to Florida, I established the first functional brain mapping and BCI program at Florida Hospital. I continue to use high gamma mapping to help epilepsy patients avoid losing their ability to speak or move after surgery. But even cooler than that, I created brain computer interface studies that let patients control things with their brain in real time. Our patients could even spell words with incredible speed by just using their brains. No hands involved. I also discovered that brain computer interfaces could help patients move their chronically impaired hands or legs years after a stroke when not much else could help them. So, I started working with the faculty from Advent Health University to help these patients restore their ability to use their hands. I received special training for it, and it's still mind blowing how cool it is. My favorite part of what I do is teaching. At my established Institute of Neuro Approaches, I've integrated all my experience and knowledge into a unique course on brain computer interfaces. With graduate neurobiology students, we started with theory, and then I gave them the BCI equipment so they could have hands on experience working with BCIs. It significantly improved the way students learn, and they absolutely love this practical part of learning how to use neurotechnology. And all of this was made possible thanks to GTech's awesome brain computer interface technology. They have everything from high tech up to 1024 channel EEG systems to wearables, tools for neurorehabilitation, such as the medical grade system recoveries and educational kits with unicorn hybrid plug for learning how to work with BCI technology. But the most important part is their support and care. I have enjoyed working and collaborating with Dr. Christoph Guger and GTEC employees for over 15 years, and I hope for many more successful years ahead. So, if you are interested in GTEC's brain computer interfaces and neurotechnologies, check out their website at gtech.at. It's worth it. And keep in mind, I do not receive any financial support from GTEC and share my honest opinion supported by many years of experience working with their equipment. Dear Neurocareers podcast listeners, welcome back to the Neurocareers Doing the Impossible BCI Award podcast series. Prepare for an inspiring exploration as we continue our journey into the cutting-edge world of neurotechnology. Today, we unveil yet another remarkable project from the laboratory of Dr. Edward Chang, building on the groundbreaking work we explored before with Dr. David Moses and the award-winning project in 2021. A direct speech BCI for decoding words and sentences in a person with severe paralysis and anarthria. And now get ready to be inspired by the latest achievement in the series, highly generalizable spelling using a silent speech BCI in a person with severe anarthria. An awe-inspiring project that claimed the third spot in the BCI Award competition 2022 and published in Nature Communication the same year. Join us as we dive into the world of silent speech BCI with our amazing guest, Chang Metzger, a visionary PhD candidate at the University of California, San Francisco, and the University of California, Berkeley. Chang's passion for research, programming, and machine learning has propelled him to explore machine learning techniques that decode speech from neural activity. But there is more to this captivating episode. Chang will take us on a tour of the real-time infrastructure he developed, enabling decoding of sentences from neural activity. He'll share invaluable insights into the neural basis of speech using neural recordings, self-supervised learning algorithms, and feature exploration techniques. As if that's not enough, Chang will be your guide through the intricacies of crafting a successful BCI Award submission and share career tips that will empower aspiring neurotechnologists to reach new heights. Tune in now for an exciting discussion on silent speech BCI and the limitless possibilities it unlocks alongside Chang Metzger's inspirational career journey. Welcome, Chang. It's a great pleasure to have you on our podcast. Thank you very much for coming. And can you tell our listeners where you are joining us from?
Sure. Thank you. That was super nice introduction. And yeah, I'm joining from San Francisco. So yeah, excited to be here.
Wonderful. Chang, can you tell our listeners about yourself? A quick introduction of what are you doing right now? What stage of career you are at this particular moment?
Yeah, sure. So right now, I am a fourth year PhD student at UC Berkeley, UCSF, with Dr. Eddie Chang is my PhD advisor. So I work with him on the BCI restoration of arm and voice clinical trial. So the Bravo trial is the nickname for that. And so I've been working there for 4 years, and I actually did a year before that as a technician. So it's kind of my fifth year involved in the project. And I will be wrapping up my thesis pretty soon. And then, that's kind of where I'm at. And we're working on kind of improving, the techniques that I'll talk about today and trying to make them work better and show that they work with, other participants as well is something important. So yeah, that's been the focus of my work recently.
Yeah, excellent. Thank you so much. And can you tell a little bit about the laboratory where you are working, laboratory of Dr. Chang? Because I think it's absolutely amazing place where such cutting edge projects are being developed.
Yeah.
So if you can give us an overview of this place.
Sounds good. Yeah, I feel very lucky to be part of it. So the lab has about, I want to say like 25 people just within the lab, as well as many collaborators outside of it. And so within the lab focuses primarily on kind of three things. So there's speech perception, so how we, listen and how our brain understands, speech during, listening to naturalistic sentences. There's a lot of great work there being done. And then there's also a production side of the lab, which focuses on, okay, how do we produce speech and talk, now? And that side of the lab actually kind of gave transition to the Bravo project, which is kind of another portion of the lab. And that project is really focused on this BCI restoration form and voice, so decoding neural activity into kind of text to help restore communication. And so that's really been the focus of the Bravo work. And so that project is also in collaboration with Ganguly, who's also at UCSF, and they do more kind of the arm restoration aspect of that. So yeah, it's a really exciting lab. And I guess for listeners who don't know, Dr. Chang is a neurosurgeon. He's the chair of neurosurgery at UCSF. And so that means that we get to work with a lot of research participants who volunteer for these studies and give us really incredible access to neural recordings. And so a lot of the lab's earlier work started with electrocorticography, so ECOG recordings from people undergoing treatment for epilepsy who just volunteered for research about how they talk or how they listen. So yeah, very exciting place to be.
Thank you so much for this wonderful overview. And now I'm very curious, how did you get to work in such an amazing place? Maybe you can tell us about your career journey and your transition to this amazing place.
Yeah, definitely. So I guess it kind of began. So I was in my undergrad at Stanford, and so I was really interested in renewable energy. But then I took a class with Krishna Shenoy, and he showed these videos of people, using their neural activity to control kind of, robotic arms. And this was really incredible to me. So, seeing not only, how excited they were to use these devices, but also just thinking about, okay, how, does our brain work to execute those movements? How can you build something to then read that out and translate it into movements? Really seemed like a very exciting problem to be working on. And so I kind of started to focus more after that class on neuroscience and machine learning to, try to help develop these BCIs and try to develop understanding of how, the brain works. I think it's really a fundamental question that's, still remains, there's a lot of unanswered questions. And so, yeah, Eddie came a couple years later. I started doing research with Daniel Palanker, who does research on retinal prosthetics. And his group, they're trying to develop like implants that slide into the retina, and basically like they're photovoltaic. So it was kind of a transition from the renewables, right? Like photovoltaics, like solar cells. You basically stimulate these like arrays with light, and then correspondingly they stimulate cells in the retina and enable you to kind of regain vision. And so that was some really exciting work. I think Henri Laroque, who won the BCI Award last year, was in that lab with me. So it was a really cool place to be. While I was in that lab, Eddie came and gave a talk, and I really liked his approach. I thought the speech decoding approach seemed extremely promising. He showed us some kind of early results from David Moses from his like very early work. And so, yeah, that got me super excited about being part of the lab. So I sent him an email. He allowed me to, do a year as a tech. And so I ended up joining the next year as a PhD student. And yeah, that's kind of how I got into the field.
Thank you very much. What do you think were those strengths that opened the doors for you in Dr. Chang's lab?
Sure. So I think a big strength was I was very passionate about the work. So I was really excited about, doing it. And I think because of that, I'd taken a lot of classes kind of as in my last couple of years, even though, I was pretty late to the field, I wasn't like taking neuroscience classes from day one. I was able to really jump in and try to take as many as I could after that. And so I took a lot of neuroscience and machine learning classes. And, this was still a time where machine learning was like fairly new. So I think just being able to take those classes and also think about how you'd apply them to brain data. And, as part of my class projects, for example, for those courses, I did, neurotechnology projects, like, recording from open source brain decodings. And so I think that really helped to show like, okay, I care about this and, I can do it. So I think that's like a good thing to try, if I guess you're interested in the field.
So what I can see that really your passion led you to your current work that you are doing, and being really inspired by this, you were taking classes, you were proactive, trying things, and you had things to show when you were joining the lab.
Yeah, definitely.
And now let's talk specifically about this project. As you already mentioned, that there are several lines of research in Dr. Chang's lab, and for some reason you chose this particular language prosthesis related work. Why was that? And how did you make this choice?
Yeah. So I think the big thing for me is that brain computer interfaces are a really exciting way to, I think, help people. I think it's something that's really rewarding to me is to like have an impact. And so this work, it's really exciting to develop an algorithm, and you're really helping someone that is unable to speak and, has a difficulty communicating, and seeing them being able to communicate again or be excited about the algorithm is really rewarding and feels like a great thing to work on. And I think the other thing that's cool about this work is that, inherently these kind of recordings are very rare, right? So we're working with intracranial, so, below the skull recordings of neural activity. And so, usually these recordings are somewhat brief, right? With the scale at which we do them. Like, there's before this trial, most ECOG was, recorded in the hospital where someone had to array for a week. And here we're able to work with our participant Bravo 1, who has now been implanted for, over 4 years. And so this is like a very exciting opportunity from, neuroscience and, just looking at the recording technology perspective to see, okay, how do things look over a long time, and, have this ability to ask questions that require a lot of data. So for example, like, can we decode brain activity in this way? Requires a lot of data. And so, it's a really exciting opportunity in that regard. So,
Yes, thank you so much. And I found it very interesting reading your paper, the one that I mentioned at the beginning, the Nature Communications. You mentioned a recent survey of prospective BCI users suggesting that many patients would prefer speech-driven neuroprosthesis over arm and hand-driven neuroprosthesis. Can you comment on that? Maybe you have more details, and why is that? Why people would choose more this type of prosthesis?
Yeah, that's a great question. So I think, speech, right? I mean, the reason that our lab targets speech decoding is it's the fastest and most natural way that we communicate, right? It's like pretty much effortless to express things. And, if we were able to build a really good speech neuroprosthesis, that'd be, naturalistic and fast. Like it's, the speeds at which we can talk to one another, like the speed that we're talking at right now, is much faster than the speeds at which, we do things like touch typing or handwriting. And so this approach, I think, is really promising in that regard. Now, that study in particular was asking about actually kind of what we did here. So if you could use a speech to drive a spelling device. And so I was actually somewhat surprised that people we're so excited, I guess, about using speech to drive spelling. But I think it goes to show just how natural it is, right? As a way of commanding and using devices, right? It's a very simple to use methodology. And so, yeah, I think it holds a lot of promise. And I think the, BCI users really care about how easy and fluid it is to use these devices and how quickly they're able to communicate with them, So I guess the field talks a lot about like decoding speed, right? But you can really see these differences when you're using the devices, right? So, the difference between 5 words a minute, versus 10, I mean, it's like double the words, and you can really, like, it's like saying 2 sentences in a minute versus 1, which really changes the pace at which you can do a conversation. Now, if you go even higher, to natural rates of speech, it's a different communication experience. So I think, the study kind of goes to show that people care about that and care about how easy and quick it is to use brain-computer interfaces.
Mm-hmm. Thank you so much. And by the way, one comparison came to my mind when you were talking about your career, how you started with the retinal cell replacement and then moved to this intracranial BCIs. We had another BCI Award guest, Dr. Nicholas Opie from Synchron, who started with the prosthetic eye. That was his first work. And then he already moved to this endovascular neural interfaces. So,
yeah.
Some interesting paths that is very similar.
That's cool.
So thank you very much for explaining that difference and this tendency for people to choose the BCI that is speech-driven neuroprosthesis. Now let's talk briefly about people whom we can help with developing such a neuroprosthesis. Who are your targeted audience?
Right. So the populations we work with are people that have, so our clinical trial participant, for example, is someone with brainstem stroke. And so he had a car accident nearly over 15 years ago. He was driving home after a soccer game and got in this tragic accident, woke up in a coma and was unable to speak. So this is because the pathways from his, brain activity in the motor cortex don't work. And so those signals are perfectly normal and they're unable to be transmitted to the articulators. So the lips, the tongue, the jaw, and larynx that, help you express speech. And so there's other conditions that result in a similar outcome. So for example, ALS, so like what Stephen Hawking had, is another common cause of this. And so that can also result in, complete locked-in syndrome. So, not being able to move at all. Our participant has some small residual movements, but not enough to speak intelligibly. And so, these conditions like this that cause, your neural activity to be completely intact, but, not be able to reach your mouth are really what we're targeting here, just because, we think that the brain activity will be similar to what we've seen in people that can speak. And so we should be able to decode it out. So that's the target.
Yeah, thank you so much. And now I would like you to walk us a little bit through your study. You mentioned already that the studies you are doing right now, these are clinical trials, yes, that Bravo trial, and you can use different ways of implanting electrodes, for example, to the area that you want to target, not that was clinically indicated if you would be doing it in patients slated for epilepsy surgery. So let's start with that. Yes. So what are you choosing now that you have a choice? What are you choosing to record this activity from the brain?
Yeah, the device we're using is electrocorticography, which we call ECOG. And so what this is a kind of credit card sized array. And what I mean by array is it's like this flexible material and it has metal contacts. And so these contacts are about 1 millimeter wide and they're about 4 millimeters apart. And what happens is my PI, Dr. Chang, he'll surgically implant those on the surface of the brain. And so they sit right on the surface. There's a surgery involved that puts in a pedestal. And so this pedestal lets us read out the signals and use kind of these recording technologies to read them out into a computer. And so ECOG has been used a lot for epilepsy. So that's why we started using it. But it became clear that it's an interesting technology for a few reasons. So firstly, we kind of saw that you could decode speech from the activity you recorded on it with some studies that happened before I joined the lab. So Joe Macon published that you could, decode text from the neural activity of healthy speakers. And then Gopala Anumanchapalli and Josh, they published that you could synthesize speech from brain activity that was recorded on ECOG. And so this gave us a very good idea that, these things were possible with ECOG. Now, the question was, okay, if we put ECOG in someone that can't speak, will we still be able to read out these signals and translate them into words, even if, they haven't spoken for 15 years? And then there's also some interesting questions about like comparing it to other recording technologies, right? So some other technologies out there would be like the Utah array. And so our hypothesis was that, those arrays are really amazing, but you record from a limited area of the brain. And so we thought perhaps having this broader coverage would be important just because there's, a lot of neural activity associated with speech production. And so having that broad coverage would be good. And then another thing that we like about it is that it's a very stable recording modality, right? So because it's on the surface of the brain, day to day, the signals look very similar. And so this is a bit different from the Utah array where, from one day to the next, the cell stops firing because those are recording from single neurons, right? Ours, and they're penetrating into the brain. So, if a single neuron drifts away or stops, firing, the signals change and you have to adapt the decoder. For us, we think because it's on the surface of the brain and you're recording each electrode, because it's so large, is recording from tens of thousands of neurons, these signals should ideally be more stable. And so, that's kind of why we use ECOG. Just, we knew it kind of that it should work. And it also has some interesting properties that could be helpful for building a brain-computer interface for speech.
Yes, absolutely. And that's a very interesting distinction that you noted. Yes, because uterine or in general penetrating electrodes, they're mostly used for motor prosthesis. Yes.
Right.
And because of the nature of language and language related areas, they are more spread out. And this approach can be more valid. And stability is very interesting. Stability of the recordings, which is a problem. Yes, right now, definitely. Stability adds here its value. So thank you very much for telling us about that. And now let's go into the areas. So how do you determine what areas should be sampled from with this neuroprosthetic device?
Yes, so that's a great question. And that was something that we determined, I think, using the knowledge we had before from kind of the work that was done in the hospital with people undergoing epilepsy surgery. So like I mentioned, so Joe Macon, Gopala, Josh, and Pengfei Sun published these works before, I came to the lab that showed you could decode text from this neural activity. And so they used some techniques to evaluate what areas were the most important. And we had, many participants that did this. So all their studies, I think had like 5 participants that had, come in and they were healthy speakers. So they read aloud these sentences from the MoCA corpus. So it's about 500 sentences or so. And so we were able to look across all these different coverages and see, okay, who has the best performance, who has best coverage, and across all these people are there electrodes that tend to be more important. And we also combined that kind of with the scientific work that the lab was doing. So seeing where, which electrodes are controlling articulatory movements, that we see just active from a basic science perspective when we, speak. And so those really helped guide our decisions with where to put the array.
So Can you maybe talk about that coverage that you used? Because I think you mentioned this, that it extended beyond the language cortex. Yeah, so can you explain why you thought that it's good to expand, or this is
Yeah.
already what you talked about based on the previous recording, so you chose the optimal one?
Yeah, that's a great point. So we targeted really the pre and post central gyri, since this is kind of from those studies where the most important electrodes are, and especially the ventral portion. So the VSMC, ventral sensory motor cortex, has been kind of shown to be the area that's controlling the speech articulators, and as well as the more kind of middle precentral gyrus, right, where we know there's some control of the larynx. But then actually, yeah, so one thing about our grid placement that you might notice is it's very kind of tilted, and that's because we're trying to cover the hand region. So that's for, like I said, our study is a BCI restoration of arm and voice. And so we're trying to actually get some hand signals. And so we've kind of tried to cover the hand region as well with our grid. And so we actually did end up using this coverage to get some hand decoding in this work. But yeah, that's something that Karanesh Ganguly's lab is focusing on doing, like just, arm decoding. What can we do with this array? And they have some great work from Daniel Silversmith that came out recently. So the collaboration had us put electrodes there, but they ended up being useful as a control signal, since they're very different from speech as well. So, yeah.
Yeah, excellent. And now about the approach that you used. So in this particular study, the spelling-based approach, maybe you can talk about it and what's the difference between the direct full word decoding approach that you used in previous study with Dr. Moses, where you were decoding the direct words from the participants.
Yeah, so in that study, the first study we did, I was decoding 50 words from the neural activity of Bravo 1. And so basically we decoded 50 high use words directly. So if you want to say I, he just say I. If you want to say am, you say am, etc. Right? And so he could just say these words and we decode them directly and put them together to make sentences. And it turns out, there's over 1,000 sentences that are possible with just these 50 words, right? Now, the problem was that, if you want to say any word that wasn't in the 50 words, we didn't really have a way to deal with that. And so it would require us recording more repetitions of him saying, that one new word just to be able to decode it. And it wasn't really something that the system was made to do. It was just like this direct word decoding approach. And so what we thought would be nice to show here is that you could use speech to drive a spelling-based approach. So, this has the natural advantage, as you can imagine, of, if you can just decode these 26 characters, then you can, put them together to spell out anything, right? As anyone who's typed knows, you need a very small set of targets and being able to hit them, and you can do really good communication and super flexible, right? It's just like every word. So, yeah, that's what we wanted to do. And I think it shows that this technology is kind of really able to be used to communicate. I think, like you can use it to say anything now. And I think it's also something that shows promise because it can be combined with that previous approach, right? Like, so you could say these direct words for high frequency things you want to say, like I'm feeling good, or, but then for less common words, you can spell them out. And so this is a unique kind of BCI then, because you have both of them. So we didn't show the two together, but I think it could pretty easily be done. And so, yeah, it's a nice addition, I think, to the previous work, and one that I think is very useful and has good promise.
This combined approach that you described as a future possibility reminded me Japanese language with the characters, and then characters symbolizing one word, yes, and then additional alphabets, katakana and hiragana, so that people can use them as basically spelling, yes, for just separate.
Interesting. Yeah.
Okay, very good, very good. That's interesting. Another interesting thing that although you wanted to have all 26 letters of the alphabet for people to use, you didn't use the letters directly, you used code words
Yeah.
for each letter. So can you explain why was that?
Yeah.
Why didn't you use just, simple letters?
Great. Yeah, that's a great question. So that was something we tried, was doing just having Bravo 1 say letters. So you can imagine, probably the most straightforward way to spell something out loud would be if you just said like HELLO to say hello, right? Now, the issue is the neural activity that we're reading out is very noisy. So, the signal isn't super clear all the time. There's a lot of like background noise and noise in the system. And so it's kind of like trying to spell over like a very noisy phone line, right? Like if you've ever been on the phone with a customer service representative, it can be really challenging to spell. And it turns out actually a lot of the words end with the E sound. So a lot of the letters, sorry. So like B, C, D, G, P, T, so it's actually pretty confusable if you're trying to like decode from, what these letters are based on neural activity. It can be a bit tricky. And so that's why we chose the NATO code words, was that, they're very easy to decode. So are not very easy, but, they're much easier than the letters. So they're designed really for working with like these noisy systems and to be extremely discriminable. So they have, kind of variable lengths and more phonetic variability. So for example, like November is in there, which has 3 syllables, as well as like alpha, right, which is just 2. And they all start with like the corresponding letter. So they are pretty easy to remember and use. And, after a while, you definitely get the hang of spelling with them. I know I got kind of used to spelling with them myself, just watching our participant use them. And so, yeah, it's definitely, I think, a good approach that helps you discriminate. And we actually have a figure in the paper that shows, the brain activity during these NATO code words is, we compare these two, right? And so with similar amounts of data, you get 4 times better performance doing the NATO code words instead of just decoding the letters. And then neurally, the data is, when you're saying each word, right, is much more distinct for the NATO code words than if you're doing the English letters. So yeah, that definitely kind of motivated why we did that. But we did try both, it's always good to try different things at the start.
Yeah, absolutely. I'm curious at how was it comfortable for the participants to learn the NATO words, those code words, and to use them?
Yeah.
What was that learning curve for them to get at the place when they felt comfortable operating those words?
Yeah, that's a great question. So when we were collecting the data, we started by just showing the code words one by one. And so for a while, they were just presented in this context of like, here's alpha, say alpha, and I think with enough of that, the participant kind of started to, really get them ingrained. And so when we did say, okay, now we can decode them, let's start putting them together to make sentences, it was actually like pretty, he didn't have a very hard time stringing them together to make the sentences. But he did, show some improvement over we did like a week of refining the system to get it to work. And he definitely, like, at first we had the speed at kind of which he was trying to type set slower, but he definitely like sped up a lot over time. And I think, yeah, I guess just personally, I like was watching a lot of this stuff, as we were developing the system. And yeah, over the course of like a week or so, it was pretty easy to like start spelling with it. And now, I mean, I guess it's been a second since we did this, but I was able to spell out fairly quick using the NATO code words. So, yeah, it's something that is pretty quick to learn, I guess. And if you can imagine too, if it was your only way of communicating, you'd definitely be able to get it super easy. And it helps that every word starts with the letter corresponding. So it's a pretty intuitive, I guess, way to work.
Yeah, absolutely. And how do you see the future of developing this type of neuroprosthesis? Do you think that you will be still moving towards using these code words, or it's possible that in the future you will be able to decode just letters as they are? And if so, what's needed to get to that point?
Yeah, that's a great question. So, I mean, I think there's many, like for that specifically, so like letters versus code words, I think it would be great if we could just do letters, right? I think they take less time to say. They're more intuitive for like, people start using right away. And so, yeah, ideally in the future, we'd be able to do it. And I think that would probably entail, I guess, a few things. So firstly, we need to see, okay, how does this look in other participants? I guess a weakness of our studies is always that it's just one participant. And so, he might be the best participant. He might also be the worst, and so perhaps with other people, it just works much better. It's one thing. And then, can we decode better using like new recording technologies? So, if we add more electrodes and make the, spacing smaller, so we're getting more signals, does that help? Like, are we able to decode neural activity, from the smaller grid with much better precision? That's something that we think might be possible. So I think that development would be big for improving, and being able to decode the letters. I think there's other things we can improve about the system too, but we can, I guess, go over that when they come up. But yeah.
Yeah. So now you are talking about improving spatial resolution, yes, of the signal
Right.
that you are getting.
Yeah.
Very, very interesting. Yes, definitely this way is more intuitive for people, and it will be very easy to use. So now people already are familiar with the code words, and you are recording their activity, and of course decoding starts. So how did the decoder work, and how did it detect the person already started spelling some words, and that they ended doing it? Yes, and that's where your motor coverage also worked. Yes.
Yeah, so I can describe, I guess, the system overview. And I guess while I'm doing this, I want to give credit to my co-first authors, Jesse and David, who built, the detection and a lot of the real-time pipeline. And so we worked together on the 50-word decoding. And so they were really helpful here too. So I just want to, I guess, shout them out. And so basically what we did was we wanted the system to be fully usable. So we wanted it to be started and stopped by neural activity. I think this is an important thing to show, like the whole system is driven by neural activity. There's not like external outputs that are being used to start and stop it. And so what we did was kind of similar to our last paper. We had a speech detector that Jesse trained. And so basically the speech detector would output the probability that the participant was, speaking at any time. And so basically, once the probability was high enough for enough time, and this would happen when our participant actually silently attempted to say go. It wasn't even trained on the word go, but that's just kind of what he liked to use. We would turn on the spelling. And so what that means is we would start to do these like cycles. So every 2.5 seconds, we'd have kind of 3 dots appear on the screen, and they'd kind of count down and then go away. And there'd just be kind of an underline. And the participant would have to say the NATO code word corresponding to the letter he wanted to say. So, for example, if he's trying to spell anything as possible, there'd just be the blank line, and he'd just say like Alpha, November, Yankee, Tango, etc. Every 2.5 seconds. And so the reason I guess we did this cued approach was this is kind of the data we trained on, right? Was we did one letter at a time, or one code word at a time, right? So it kind of made sense to put them together using this kind of cued approach so that we could kind of directly use the model that had been trained on the cued data. And so, what the model does is it basically predicts 27 classes. So 26 of those are the code words, Alpha, Bravo, Charlie, etc. And then the last class is the probability that he's trying to do this attempted hand squeeze. And so that's where we take advantage of, that motor coverage. And if the last class has a probability greater than 0.8, then we say, okay, that means he's trying to stop doing the sentence. And if not, we save, the probability of all the NATO code words, so corresponding to all the letters. And we like kind of build up this matrix time step by time step that, says, okay, how likely is each of the letters? And so what we can do then with that matrix is what's called like a beam search. So we look for the most likely path, but during that beam search, we also use a language model. So we're using like an n-gram language model, which basically says, okay, given the last n-1 words, what's the probability of the next word? And so this lets us, say what sentences are more likely versus not. So for example, like, hi, how are you is very likely versus hi, like, cow are you would be like less likely with the language model. So it helps kind of correct or say what's more likely, because our neural decoding isn't perfect. It's actually only like 54% accuracy if we don't use the language model at all. And so having that really helps kind of correct. And then we're also actually, I should mention, adding vocabulary constraints at this point too. So one nice thing about spelling is, there's kind of rules. Like you can only spell, there's like a set number of words, right, that are possible to spell. So we know right away, like CXT is just not possible, right? So we have a checking at each point in this beam search as we're adding these letters. And this is also something we're doing, in real time is, is this word possible? So that helps us kind of narrow down. And so we actually go from this like just over 50% decoding, without these language models or vocabulary constraints to really high accuracy. So I think it's like 94% after we do the constraints in the language model. And then one other thing that's happening, so this part is, I think, the meat, I guess, of the process. There's also no NATO code word for space. And so that process is automatically inputting where the space should be. So basically, based on, what words are possible, what we do is we say, okay, how likely is it if we had like a space after this character, as well as if we just added this character to each beam? And so then we can see, okay, if there's a space after, does that form a valid word, right? Because the space delimits when words are. So yeah, we add spaces and kind of check like, okay, does this work? And so that way we can automatically add the spaces. And so it saves our participant a good amount of time, actually, because then you don't have to, take the 2.5 seconds to say an extra code word, which might be missed. So I think this is a nice aspect of our system. Now the beam search, will take kind of this stacked up probabilities of all the code words, put in spaces, make them into like intelligible words. And then afterwards, he attempts to squeeze his hand, and the process stops. And so then we pass all these. So we have like a list of basically 1,000 possible sentences given the brain activity. And so then we rescore these sentences with like a big language model. So we use Distill GPT-2, which is kind of a small, low parameter version of GPT-2, which I guess was the precursor to all those big models you hear a lot about today. But that helps us kind of use more context and really improves the predictions as well versus using just the n-gram model we have, because it looks at, all the sentence at once. And so that's kind of overall the process. I think one other thing I should mention that's very important here is this is driven by silent speech activity instead of overt. So the previous paper we had, right, that was doing the 50-word decoding was our participant had to like attempt to say the words out loud. So he had to activate his residual vocalizations, and it was really hard for him, or not super hard, but, it was effortful and definitely kind of limited the rate at which he could do this. And so this is completely silent, which is nice. It's less effortful, and it's something that can be used discreetly too. Like, that's kind of the overview of the system.
Yeah, absolutely. And it's very impressive how you improve the decoding accuracy. Yes, from 54 to 94. Oh, yes.
Yeah.
94 was, that's absolutely amazing. And you explained, of course, the ways you improve that accuracy. Maybe you can just summarize in like bullet points. What did you do to improve that accuracy? Yes, from the initial 54 and then, getting to such a high accuracy.
Yeah. So I guess bullet points. So firstly, we have the vocabulary constraints. So we say, okay, what words are possible? That helps correct errors. So if the decoder says this code word should have been like Zulu, right? So like Z, but we know the first one was definitely C, and the one after was definitely T. We say, okay, no, that's not possible. CZT is not a word. So that helps correct. And then we also, beyond the character level, we look at how the sequences of words look and how likely they are. So like the language models, I guess, help add that second correction. So basically saying, okay, like this sequence of words makes sense and is something you would see in a book or in Twitter is what we train our language models on. So having that is also the second layer of correction. So these actually really help improve the accuracy a lot. So.
Thank you very much. And you also mentioned that you use the language model GPT-2.
Mm-hmm.
What do you think would be possible outcomes of using later models? And, in general, the new approaches, new models that are developing so rapidly at the moment.
Yeah, that's a great question. So, I mean, one thing you could do is just feed it kind of the like most likely predictions at each time step and say, all right, what's the sentence from here right away? And I guess skip the beam search would be one thing you could try, although I'm not sure how that would work. But I think a really exciting thing is like the zero shot or one shot capabilities of these new language models. And what that means is basically you say, like translate from English to French is an example of like a zero shot prompt. And then you put in a sentence and it'll make it in French, right? So these models have like these really amazing capabilities like that. And so one thing you could do with ours is like something like that, right? Where if the participant wants to use it in a different language, they could put that in right at the language model phase and just do it. Another thing would be, incorporating more context, right? So if someone has just spoken to the participant and says, hey, how are you? You could put this context into these like better language models and say, okay, like someone just said, hi, how are you? What would they say in reply? And kind of help morph the responses that way. So I think there's a lot of really exciting possibilities, like using these better language models with neurotechnology. And I think, the participant could also cue like where they are into them. So I think it should be very interesting to see how that work gets, put into the latest brain-computer interfaces.
Absolutely. And what inspires you in the current technological developments? What would you personally would like to implement in your work?
I think there's a few things. So first is this like self-supervised learning I really like. And so that work is basically learning without labels, right? So an interesting part about developing brain-computer interfaces is it's not like training a language model where you go online and you scrape websites and that's how you get your data. And so it's basically instant and it's there. Like you have to sit down with a participant, for like 4 hours in a day and have them say these words, and so like for the 50 words or for this project is really intense. Like he says the code words 9,000 times, right? And so this takes a lot of time. You can imagine it's pretty tedious to use. And if we want to keep using the activity, say he's using this device like every day, right? Like how do we use that brain activity, if it's not labeled, like how can we use that to train the model and keep improving it? And so I think this field of self-supervised learning is really cool because it would let us use, unlabeled activity while they're just using the device to improve model performance. And I think that's really exciting and would be really helpful to the participant where, he doesn't need to, sit down and do these training sessions. I think would be cool. And I think it'd be also really amazing, as more participants join the trial and using data from the people we worked with on earlier studies, who had epilepsy. I think making this more general, which I think self-supervised learning could be a good way to do that. So making it very easy to transfer across participants is also super exciting. So like from a kind of decoding standpoint, I think that would be really awesome. And then I think we also really want to make it faster. So kind of moving away from a spelling approach and towards something like our first project, right? Where you're decoding natural speech, but in a way that is more generalizable would be really cool. So for example, I guess a lot of like ASR, so automatic speech recognition, what they do is they actually use a spelling approach. But it's like on you saying sentences like this continuously. And so the model really just learns how to output sequences of, subword units, so characters or phonemes, and then put those together to make the sentence. And so you get kind of the benefits of both our papers in one. So you get the direct and you also get generalizable. And so I think if we were able to apply that to kind of our work, that would be super exciting.
Yeah, thank you so much. So you have a lot of work ahead of you.
yeah, a lot of work.
Okay. And one more thing that interested me when reading your paper, that You looked at both low and high frequency components, yes, in your data.
Yeah.
So can you comment on that and maybe to give our listeners some context, about the high frequency components that were mostly used before? Yes, so why
Yeah.
was it done and why did you take a slightly a different approach of using also low frequencies?
Yeah. So for high frequency, like the high gamma activity, that's just like well, I guess it's not just been used. Like, so there's studies that show that it correlates to synchronized firing of neurons, right? So, when like these electrodes are fairly large, and so you're recording from tens of thousands of neurons. And so when they all fire kind of in synchrony, that's correlated to this response in the high gamma range. And so the high gamma activity, so, we record a raw voltage on the electrode, and then we filter out activity between 70 to 150 hertz. And so that's the high gamma that we end up using. And so, yeah, it's been shown also, in our previous work that high gamma activity is very correlated with like articulatory movements. And you can decode articulatory movements from that high gamma activity in healthy speakers. So we kind of knew that this is a signal that's very relevant to speech. And so that's why we really focused on it, both in this study and our previous study. As far as the low frequency activity goes, a lot of motor decoding work, as well as some speech decoding work, like Gopal and Josh use these low frequency signals, where we know there's also rich motor activity. And so we were able to kind of use these to improve our decoding, started using a different range. And it really added a lot to the high gamma activity. And so we saw that, it let us kind of get meaningful signals from these electrodes that weren't contributing much from high gamma. They actually had a lot of signal. And the signal was actually it had pretty good spatial components, right? Like there's a lot of spatial components, actually more than the high gamma even, which was a big surprise. And so that showed that we were kind of able to get more activity from across the brain using this low frequency signal. And I think one of the bigger surprises for a lot of us on this paper was that the low frequency signals were more decodable than the high gamma actually. So that was a kind of the big surprise. But then luckily, when we combined the two, they were the most decodable. So that was nice. And we did some work that showed, why that is. So like I mentioned, right, like some of the electrodes that aren't contributing much to high gamma are really helpful with the low frequency signals. And so I think that was a cool part of our paper. I hope that, anyone using ECOG uses these bands now. They're super helpful.
Yeah, yes, absolutely. And also help you to improve decoding. Yes, one more bullet point that we can add.
Yeah.
Excellent. And now you mentioned that was one thing that surprised you in the study, yes, that low frequency components were even more decodable than high. What else surprised you? So what was the biggest surprise of the study that you did?
Real quick, I'll add, I guess for people listening, I'm looking at the figure now. So I guess just the high gamma is like 30% accuracy, low frequency is 45, and then high gamma plus low frequency is around 55. So that's just to give you a sense of the improvements. But I guess the biggest surprise, honestly, it was getting to know our participant a bit better through when he was using this. Like, so we've been working with him for 3 years, but, he can't speak. So we say a lot of stuff and, we definitely know him, but just seeing him use the device, we got to learn a lot of, fun stuff about him and get to know his personality more. So that was, I think, a really nice surprise, was just how effective it was at getting communication with him and learning more. So that was really, I think, the best surprise. I think the other big surprise too was, I guess, using the NATO code words, how big of an improvement that was. And then also, how, we don't need the perfect decoding accuracy, right? Like we're decoding these code words with 55% accuracy. You would think maybe that's not useful, but when you put them into the system, that they can be extremely useful, and adding these contexts helps so much. I think that was also a really cool surprise. And then I guess the last surprise was that it didn't matter like how big the vocabulary was that we were constraining during the beam search. So we initially used a vocabulary of just over 1,000 words, since that accounts for around like 85% of spoken language, like, most of the words we say are very high frequency. So that's why we targeted that. But, if you go up to like 9,000 words, it makes no difference. So that was also really an exciting surprise and shows, we're not just relying on this like small vocabulary, or not small, but, a more constrained vocabulary to see good decoding.
Yeah, and that is really very impressive. The importance of communication. Yes, you said that you knew the participants for 3 years, but when you got to really communicate, when he was able to say so say words, then it helped you to get to know him much better.
Yeah.
So it's a huge value, just demonstration of that value of and of the work you are doing is creating those neuroprostheses. That's amazing.
Definitely. Yeah.
So all those things that surprised you. Now, what was the most challenging part of the project and how did you solve this challenge?
One big challenge was just decoding the silent speech. It's definitely a little bit harder than doing the overt speech. And so we have a figure in the paper that kind of really compares these two. And I think that, without the low frequency signals, I don't think that actually would have been high enough to get very good, decoding. So we had 55% accuracy. I think if you go like a bit below that, you stop being able to see that jump, right? You need like a certain level of accuracy to be able to use the language model and the vocabulary constraints effectively. And so I think, using these low frequency signals and getting that accuracy to a place that we could use it. So, having to collect a bunch of data was important. And I think also a big challenge too was figuring out, okay, we have all these models, that were trained on the single words. Now, how can we use these models in a system, right? And so I think that was something that perhaps maybe we'd change next time, would be like, okay, instead of training these models on him saying a single code word at a time, it would have been nice to have them on like him saying, the sequence of code words to say the sentence, but we weren't really sure how we were going to put the system together. So I think, building that up and saying, okay, this is how we're going to do it, and being able to have it work like that was a challenge. And putting it all together and doing it in real time was tough. And thanks to, I guess, David, Moses, and Jesse for their work on that too. That was really helpful. And another thing, right, the hand motor command, right? Like, so, okay, how do we have this work? Like, we originally were going to have the hand motor command be a space, and then we're like, okay, we can just do that automatically. So now let's use it. And then like, how do we end it? Right? Because if you end it too early, like the error rate's really high. Like if you like end it after like 2 letters, by accident, it's just like, that was 2 letters instead of like, this whole sentence, like almost 100% word error rate. So those were kind of really important decisions as well.
Yeah, thank you. And for our listeners, I think it would be very important to emphasize the significance and also challenge of making this work in real time. So can you explain what is that difference? Why is it difficult to make the system work in real time?
There's a few things. So firstly, we train these models before we show up to the participant. So they have to work, the next day. So that's the challenge is, making a model that's robust based on, historical data that it'll work, the next day. And so we use a lot of data augmentations and collect a lot of data to be able to do that. I think the next thing is, you have to run all these processes in real time, and have it be like a, kind of usable device, right? So like, offline, you can just like say, okay, we'll stack all the predictions together as he says words from these, code words from these sentences, and it'll work, But in real time, you have to say, okay, no, you got to say them at a certain rate so that we know when you're saying each of them, and we have to then take these predictions and run the beam search, and do all these processes like in real time, and like we display them in real time back to the participant. And so there's like this usability factor that's important. You can't just like throw together your predictions and models. Like, someone's using the device and you want it to work. And there's also, speed considerations there, right? So for example, like I mentioned, we use the distilled GPT-2 right at the end. So it'd be great if we could use it, at every time point, right? Like instead of the n-gram language model we're using, which is way more basic. But that one's fast enough that we can just do it a bunch in real time. And then the still GPT-2, which takes a while, we do at the end. So that's like, okay, yeah, like now we've got it. We'll take a second, to run it once. So that I think is another kind of consideration, like getting these things working in real time. You have to make some trade-offs that if you were just going for pure performance, you might not need to make.
Yeah, thank you. And can you now summarize the results of the study?
Yeah. Overall, our results were just that we were able to, decode sentences from, the participant attempting to spell using the NATO code words with high accuracy. So our character error rate was 6%. So that means we had about 94% accuracy in terms of the characters. And our word error rate was 10%. So that is like, on the word level, how accurate are we? So that's about 90% accuracy. The speed that he was able to do this at was, just over 29 characters per minute. So pretty good speeds. And it was over 6 words per minute. So around 7, actually. So I think it was like 6 point something. Yeah, we'll say close to 7. And this was cool because, the device he was using to communicate before the study, he was at much lower rates than what we showed here. So an improvement kind of over the way that he was able to communicate. And so, yeah, I think overall, this study shows that, you can use decodings of these NATO code words and put them together to make, a speech-driven brain-computer interface that can be used to spell out sentences in a generalizable way.
Mm-hmm. And how is it compared with the studies that were done before? Because there were studies with the commands from motor cortex, yes, cursor movement, yes. So, how is it compared?
If you compare it to the kind of cursor control, we're about the same speed in terms of the characters per minute. So, the Pandarinath et al. Paper, where the participants are controlling cursor on a screen, I think we're a little. It's like basically the same characters per minute. In terms of the handwriting paper, we are definitely below that. I think they're at 90 characters per minute. That's really impressive work. Now, the thing is, I guess we have the speech option, right, that you could use. And I think the speed is something that we could also improve too, right? So because we had this queuing system, I think if you were able to kind of fluently say the words without having to do the kind of 2.5 second timing, hopefully we could see some improvements and make this faster. But I think it's a good start. It's a proof of concept for now, and hopefully we make it up there with the handwriting. But that is some really amazing work. So but I think it's just a development. And hopefully we see some improvements soon.
Yeah, absolutely. It is a very impressive work, and maybe you can say what became possible with this study that wasn't possible before.
Yeah, so I think a few things. So firstly, I think this really showed the decoding of silent speech was possible, right? So and before this, we didn't know, if this was a usable control modality. And I think showing that this does work is important because, not all patients will have residual vocalization, right? Like our participant does. And like, even though it's not intelligible, it's still, potentially provide it's just showing that we can work without it, I think is important. And I think it shows that it's a good control modality. So I think that's one big thing. And then I think, showing that speech BCIs can be used in this way that enables, real and large vocabulary communication is also very important. I mean, I think, our previous study was a great proof of concept, with the 50 words, but I think here we really show this is something that, increases the clinical viability of a speech-brain computer interface. Like now it's something that you could more realistically see yourself using day to day to, say a variety of things rather than just, having this like very constrained 50 words. So I think, it really shows this is a, feasible device that could really help people.
Mm-hmm. Thank you. And if you can summarize, what were the most innovative approaches that also haven't been used before that you used in your study?
Yeah, for sure. So I think, I guess we used like deep neural networks to do the decoding. So I think, these have been used, I guess, throughout, and we used them in our previous study, but I think, they're still pretty new. And so using those was important. I think The features we used were innovative. So yeah, we spent a lot of time kind of refining the features, right? I think our previous paper, we'd focus a bit more on the models, and then we were like, okay, this model is pretty good, but I mean, I think a big lesson I've learned is the data is more important. And so the features we extracted and also what that data was using the code words instead of the ABC was really important. And I think fusing these with the large language model was also super helpful. So yeah, I would say those are the innovative parts of it.
Okay, thank you. And what would be your suggestion to people who want to get into this field? They want to get involved in studies like that. What would you recommend?
Yeah, so I guess I'd recommend, trying to, I guess if you're like a current student, get involved in research. So I think, being part of the Palantir lab was really good because, I mean, then you're doing the work, and I think you get to experience if it's something you want to do long term, and yeah, get to really be part of the research. I think is super exciting. I think, if you don't have that opportunity maybe available, try to look online for these open source data sets, that people release. So for example, that handwriting data set, that paper, they did a great job of sharing it. And we want to share our data like that moving forward. And so I think there's a lot of, neural recordings online that you can access and, get your hands dirty doing that decoding. And yeah, I'd say to take kind of the available neuro and ML courses you have. And then Coursera also has a lot of really good classes. So I learned some of the stuff I use in this paper from the Coursera natural language processing class. So, if you feel like there's any gaps, I would say just be proactive about finding resources online. There's really great stuff to fill those in.
Yes, absolutely. I'm so grateful that you pointed that out, that there are so many data sets available that can be analyzed. And
Yeah.
definitely people can get into the field by doing that and adding this information on their CVs, demonstrating that to potential employers or supervisors that they're basically ready to do the work. So,
Yeah, definitely.
yeah, that's a
Yeah.
great point. Now, moving forward, what are your plans? What are your next steps that you are planning?
Yeah, so I'm planning on graduating in a bit. So I'm working on, wrapping up the thesis, putting that together. And yeah, that's kind of my next steps for now. Yeah, and then I'm planning on doing, I guess, visiting researcher position after that. I'll be working with Chang and King. We're trying to do similar work non-invasively and trying to show that it could be possible without a brain surgery, which I think would be a great benefit to the participants in these kind of studies.
Yeah, absolutely. And this is also some way to go about using BCIs not only for clinical participants, but possible and for people without certain problems who can also communicate in this way,
Right.
maybe silently with
Yeah.
each other. There are situations that might require that, and we might be looking at a completely different way of communication in the future. So, and my question is for you, how do you see the future of this type of neuroprosthetics or in general brain-computer interfaces for communication, for language in the future, let's
Yeah.
say 50 years from now, maybe 100 years from now? I don't know. You can choose the timeline.
Yeah, that's a great question. So I think it's a really exciting time for the field. When we're talking about these devices, right? So the handwriting, so that group also recently did a speech decoding paper as well. That was in the BCI Award. I don't know if you guys have done a podcast, but yeah, super exciting. And, our work. But these are all devices that are very old, like these recording technologies have been around for a while. So it's exciting to think about, as the hardware improves, just how much better we should be able to see this technology get. And so I think hopefully, in the next 5 to 10 years, we start to see this be a really solid and usable solution for people with paralysis. I think that would be an amazing goal. I think for now, it seems like the invasive approach is the most promising based on what we've seen. And I think, being able to really see this technology go from like research to actual products should be possible. And it will be really exciting to see how that turns out in the next 5 to 10 years. And then, yeah, I think what you were saying, like potentially having it be used by non-paralyzed users. I mean, I think these brain specific ones are still a ways away, but I think definitely something we're seeing more of, right? Like consumer neurotechnology is starting to pop up, and things like control labs, right? With like these wearable EMG sensors, as well as like companies like Neurable. There are starting to be some interesting developments there. So yeah, I guess we'll see how that works out too. But I think it's a really exciting time, and it's exciting too to see how therapies are being developed for like other conditions like depression, for example. There's a study from our group on that, which is extremely promising. So yeah, I think very exciting time.
Yeah, thank you. And now, because we are recording this BCI Award series specifically, can you share your path to your BCI Award, to getting your winning place, third place in the BCI Award 2022 competition?
Yeah. Yeah, that was our second application. I guess we did one the year before for the 50 word. And so really what we thought about was like, we took kind of the papers and we condensed them, really tailored kind of around the scoring criteria. So there's like a scoring criteria on the BCI Award page. So they say, okay, does the product include novel application, new methodological approach, benefit for potential users, improvements in terms of speed, accuracy, results from real patients, work online in real time, improvement for usability, and new hardware. And so luckily, our project ticks a lot of those boxes both times, but I think just emphasizing that in our submission to really highlight, that this is what our project is doing, or like this is how our project is like new, or like this is how it's, methodologically different, and et cetera. So really just trying to hit those points and emphasize them was very important. And I think trying to make it clear and really focusing only on the key results, not going too deep on kind of these like side analyses that are maybe like figure 4 or whatever, so just like really focus figure 1, 2, kind of like the key takeaways. And then, having a nice video too helps. So we usually try to make something that's cool and compelling.
Yeah, and it's very interesting that you said it was the second submission.
Yeah.
And you didn't stop. So after the first submission didn't win, you didn't stop. You decided to submit again. Can you share with our listeners why did you think that it's important to try it again? Why didn't you stop?
So I guess our first one, I think it got second maybe, but I think it's just like, it's good to always just submit, there's no consequence of not winning. So you might as well try, so yeah, I guess my mom always says like, you've already got the no, so may as well try it. And I think it's always a good practice to, think about these scoring criteria and how they relate to your project. Because I think these are, important criteria for any BCI, like showing why they're good and important. And I think, the whole field, like these are kind of the metrics used by the whole field, right? Like how does this compare? And so I think it's a good practice just to do it, even if, you don't win, just, condensing the research, communicating it, and thinking about these criteria, I think is really cool. And also, you get to see a lot of amazing work just by like checking it out and seeing the award ceremony. I mean, I know this last one, I was really blown away by what I saw. It was really, really amazing stuff. So yeah, it's cool.
Yeah, thank you for sharing that. And it's indeed an amazing learning experience that you can use and for the future grant writing. Yes, the ability to communicate your work in simple, understandable terms and making it successful. And it all require practice.
Right.
I remember the Synchron, they submitted their project for a number of years, and finally it won. And it also concerns many other submissions. So it's just a possibility to have this learning experience that finally works.
Yeah. And one year you might have like a new result, that takes it over the line. So yeah, always worth trying.
Yeah, absolutely. And what do you think were the outcomes of your submission in terms of learning, in terms of maybe making your research more available to people? So what do you think were those main outcomes?
I think, the big outcomes were, I guess, thinking about the key results, right? So like if we had to just do, we don't have 6 pages and 30 pages of supplement. What should someone take away from this? And so thinking about, the paper and what it means, I think is really a good practice. And so, yeah, it helps you kind of talk about it in short form, which I think is always an important skill. And then also during the, I guess, presentation, and that's also, another good time to practice and making a very quick and accessible and clear presentation, and thinking about why your project, I guess, should win is a good thing. Like thinking about what the rest of the field is doing, and what you can take from other people's projects to improve yours and their directions, I think is also a good practice. Like thinking in that like competitive way, it can be a good practice. It doesn't always feel like a competition. So I think having that aspect sometimes can be nice.
Yeah, it's more facilitation than competition. So
Yeah. Right. Sorry. Yeah. Maybe that's a bad, but yeah, it's a good way to see a lot of really awesome work. So
yeah,
yeah.
absolutely, absolutely, and together with developing skills. Yes, excellent. So now that our podcast is going almost to its end, one more question I have, which I ask usually all our participants, it's about doing the impossible, because that's our podcast, Neurocareers, doing the impossible. Maybe you can think of any situation in your whole career, not necessarily just in this project, when you thought that something just might be impossible, but you persevered and you proved that it was possible. If you can remember something like that, and how did you make that impossible possible? What would be your advice also of making the impossible possible?
I think the thing that immediately comes to mind is with the 50-word paper. So like after like a week or two of collecting that data, we were at like 10 to 20% accuracy. And we were just like, I don't know if we can do like 50 words. We were like, I think it might be too much. So making like a learning curve. So seeing how much the data was helping our model, and then really refining the models, like gave us just so much improvement. And doing these, like, we found a few things that really helped it. So like downsampling the signal. I guess this sounds very technical, but like really it was just like sticking with it and being like, okay, no, I think let's just try everything we can as a team, to get this to work. And I think also trusting that more data was going to help. I think with deep learning, more data is always the answer kind of. So trusting that, like, okay, yeah, we'll just double the data and we will be way better than 20%. So yeah, I think just trusting in the data, and, making refinements, even though it felt like we were kind of stuck for a bit. Like we were kind of like had plateaued a bit, and then we improved the models and it kept going up and improving. So yeah, I think just sticking with it and trying everything, like and trying some things even twice, like, because you might have messed it up the first time, I think is also important. So yeah, just really keep trying things and experiment quickly, I guess.
Yeah, excellent. Thank you so much, Sean, for this absolutely amazing
Mhm.
podcast. Is there anything you would like to share with our listeners? Any advice you want to give, or just say anything before we end our this podcast?
Yeah, I guess it's an exciting time. I think just, yeah, try to stay up to date with everything, and yeah, keep refining the skills. Always good. And yeah, good to practice and implement things you like. I think that's always super helpful, doing stuff. It's really a key. So yeah, but yeah, thank you so much for having me on. It was really great to be here. And yeah, thank you so much.
Yeah, thank you so much, Sean, and I wish you all possible success and all the amazing work you are doing. And I hope to see you in our future podcast episodes, because I know that there is so interesting development that is going on
Yeah.
in the research projects in the lab. So I look forward to having you again as our guest and sharing your research with our listeners. So thank you very much.
Yeah. Thank you. Thanks for having me.
Are you a fearless pioneer in the world of brain computer interfaces? Do you have an amazing project that's pushing the boundaries of what's possible? Then we want to hear from you. The International BCI Award is one of the biggest and most prestigious awards in the BCI world, and the deadline for submission is September 1st. But don't worry, you don't need a top-notch budget or equipment to be a nominee or a winner. All it takes is a great idea and the determination to make the impossible possible. So, submit your project now at bci-award.com or find the link in our podcast notes and join us on this incredible journey to explore the world of BCIs. And make sure to listen to our upcoming BCI Award Neurocareers podcast series for tips and tricks on creating a successful submission. Who knows? You might be the next nominee or winner of the International BCI Award and proudly showcase your nomination on your resume to impress potential employers and establish a successful career in neurotechnologies. But don't stop there. If you're looking for more guidance on succeeding in neurocareers, book a free consultation with me, your podcast host, Dr. K, at the Institute of Neuro Approaches. So, what are you waiting for? Let's make the impossible possible together.